So, we are discussing about link budget and then link margin, and we concluded that at least a value of 3 dB to 10 dB link margin should be maintained for any given receiver system. So, we will take one numerical example how to calculate link budget and link margin. So, before that we will be using this formula simply. So, here PL a function of R, this PL it represents actually the path loss. So, here in the table free space path loss we are considering by L naught, and in decibel scale we represented it by PLR. So, let us say we have a geostationary satellite link that operates over 35 to 36 gigahertz band with a transmit carrier power of 120 watt, transmit antenna gain given as 34 dB, IF bandwidth 20 megahertz, maximum distance 39,000 kilometer. So, it is a geostationary satellite. So, typical separation 36,000 kilometer, but it can change with time, and here it is considered maximum value as 39,000 kilometer. Then the receive antenna gain it is given as 30 dB and has an effective temperature TE equal to 100 Kelvin. So, what is the effective temperature we will discuss in next class. After this, the required minimum signal to noise ratio SNR 10 dB. Then we need to check now for a link margin at least 3 dB value is there or not. So, what are the data given here? Operating frequency, if I go back to previous expression, transmitted power is given, gain of the antennas those are given, path loss we can calculate. For that we need lambda, and the distance is already given 39,000 kilometer. Now, lambda we will be considering the midband frequency that corresponds to midband frequency. No data is given for the line loss. So, for now we will simply neglect these terms. Then if I consider at least 3 dB link margin, so minimum SNR required at the output of the receive antenna is 10 dB plus 3 dB, so 13 dB. Now, we will check what is the received power PR, is it at least 13 dBm, 13 dB or not. So, we will start from path loss calculation. This is 20 log 4 pi r by lambda, r is given as 39,000 kilometers. So, it is 39 multiplied by 10 to the power 9 divided by lambda value 0.00845 meter. So, you can calculate what is the free space wavelength at 35.5 gigahertz. It would come 0.00845 meter. Now, path loss in decibel scale, then it comes to 15.3 dB. We will convert all this data to decibel scale. It will be easier for calculation, then it would become simply arithmetic addition and subtraction problem. So, transmitted power PT 120 watt, this is equal to 50.8 dBm. So, dBm it is with respect to milliwatt power. How we represent in dBm? Any power P, it is first simply divided by 1 milliwatt, and then we take the we convert it to decibel scale, that is the unit then we call dBm. So, that means for this 120 watt, how we can calculate it? You simply divide 120 divided by 1 milliwatt, that means 120 divided by 10 to the power minus 3 then you take 10 log of that value, it would come 50.8 dBm. Then the received power, this is the transmitted power. So, we are simply using this previous formula, only thing is that we do not have any value given for LT and LR, and we are assuming them here as 0. So, if we put the values, it is coming minus 100.5 dBm. We can also represent in terms of watt again. So, just back to watt value, 8.91 into 10 to the power minus 14 watt. It is so small, the received power. It is a satellite link 39,000 kilometer away. So, SNR at the output. So, for this SNR calculation, signal to noise ratio. So, signal power whatever we are receiving, that is PR 8.91 into 10 to the power minus 14, and noise power, it depends on the effective temperature, effective noise temperature TE of the receiver, and the bandwidth of the receiver. So, this bandwidth we will discuss later. Again, this bandwidth is not simply the bandwidth of the channel. For now, we are considering bandwidth of the channel, which is given as the IF bandwidth 20 megahertz. So, put the values here. K is the Boltzmann constant, which is 1.38 into 10 to the power minus 23. So, if I put the values here, it is coming 3.23, or if I convert it to decibel scale 10 log 10, it is coming 5.09 dB. What was the required SNR? 13 dB, and what we are getting here 5.09 dB. So, the receiver, it can't sense this incoming signal. Then what is the solution? At least this SNR we have to improve to 13 dB. So, only control where we have, either we have to increase the transmit power or antenna gain. It can be transmit antenna, it can be receive antenna, but we have to increase the gain. And another interesting thing, that noise, it depends on temperature. So, we can cool down the receiver to decrease the noise component. So, these are the external control we have. We do not have any control over separation, distance, and IF bandwidth, it depends on application. So, again we can't we can't decrease the IF bandwidth. So, we have to only play with them with the transmit antenna gain, receive antenna gain, transmit power, and the receiver temperature. Next, before starting the next part, let us discuss the digital modulation, popular types of digital modulation. Digital modulation, they are popular because they have certain advantages over analog modulation. And from millimeter wave perspective, we will discuss what are the effects we face with digital modulation. So, why we use digital modulation? What are the advantages over analog modulation? It has superior performance in presence of noise and fading. And not only that, if I compare the total power required for any transmission channel, it would have low power requirement compared to any analog channel. This power requirement, it depends on modulation scheme, we will see. Then error correction, this is not only for digital modulation, for any digital system we can incorporate a way so that we can understand there is any error in receive bit chain or not. We can also encrypt our data, which is not feasible in analog communications. So, because of these many advantages, now digital modulation, it became very popular inside your mobile phone or even in a handheld devices. Mostly we are using now digital modulation, and here are some typical digital modulation example. The first one is amplitude shift keying or ASK, where simply when any one state will represent when the signal is present, and 0 state we represent when there is no signal. So, we have a bit straight here given by 1 0 1 0 0 1, and now we are modulating it and representing it in ASK. The second one is frequency shift keying. Here we use two different frequency components to represent 1 and 0. You can see 1 is being represented by a lower value of frequency, and the 0 component it is being represented by a higher frequency. And in PSK we call it phase shift keying. A change from 1 to 0 is represented by a change in phase. A conventional PSK, it will change the phase by 180 degree. We may use there are actually higher order phase shift keying scheme like QPSK. In QPSK or quadrature phase shift keying, we use 4 phase shift values: 0, 90, 180, 270 degree. We may have also higher order coding, higher order modulation scheme using phase shift keying. In addition to phase, we can also control their amplitude. In that case, we call it QAM or CAM signal. Now, let us see how the bit error rate it varies with the signal to noise ratio of any bit. So, bit error probability, it depends on the ratio of received bit energy. Received bit energy is being represented by EB to noise power density in the channel, which is N naught. So, EB, which is bit energy, it is then S into TB. So, S, it is the received signal power. This is for the carrier in general, or we can represent it in terms of bit rate. Let us say RB is the bit rate, then EB is equal to simply S by RB. This is watt second unit. Then SNR, EB by N naught, this is equal to STB by N naught, or we can also write down in terms of RB, S by N naught RB, and this is, let us say B is the bandwidth of the receiver, then N naught, this is equal to total noise power N divided by B. So, it can be also represented as S by capital N B into TB. Now, we see some theoretical calculation, comparison of bit error rate considering coherent demodulation, the variation of bit error probability with EB by N naught in dB. So, for different digital modulation schemes. So, for ASK, what we see, for a given SNR value, bit error probability is highest among these three, or in other words we can say that for a specified bit error probability, BPSK or QPSK would require lower SNR value, EB by N naught. Here is a chart for different modulation schemes. The minimum required EB by N naught value for given bit error probability of 10 to the power minus 5. So, we want at least a bit error probability of 10 to the power minus 5, then what is the minimum SNR we need to maintain for different types of modulation schemes? For binary ASK, it is 15.6 dB at least, binary FSK 12.6. So, binary PSK and QPSK, these two, among all these, for them we need minimum SNR signal power 9.6. If we go for higher order modulation scheme, again the required EB by N naught increases, then why should we go for higher order modulation scheme? Because in that case the effective bandwidth or bandwidth efficiency, we can say, it can be increased. Let us take one numerical example. So, what we see before taking the numerical example from this graph, that if signal to noise power decreases, so noise power, it depends on temperature and bandwidth. If noise, so noise power more or less it will be constant. Now, if signal power decreases, then what will happen? Bit error probability, it will increase, error will be high. So, for a given data rate, we need to maintain some minimum SNR for a given modulation scheme then. So, let us take now that example. Let us say an UAV uses QPSK to communicate with its base station, and base station is r equal to 100 kilometer away. So, UAV, it is a flying object. Then what is the maximum data rate for a bit error probability of 10 to the power minus 5? So, 10 to the power minus 5, then what is the required EB by N naught? We have to first see from the chart. So, EB by N naught, if I go back in this table, it is given minimum bit error as 10 to the power minus 5, minimum EB by N naught required is 9.6 dB. So, 9.6 dB, if we convert it to simply ratio, it is coming 9.12. Now, other data, given that transmit power is 1 watt, carrier frequency 77 gigahertz, transmit antenna gain 10 dB, receive antenna gain 30 dB, and the system temperature 750 Kelvin. We also have some atmospheric loss 2 dB, and required link margin is very high, 10 dB. We start from path loss calculation. Path loss, this is 20 log 4 pi r by lambda. So, r, this is given 100 kilometer, and now lambda, this is lambda naught at 77 gigahertz, which comes 0.0039 meter. If we put the values here, path loss is coming 170.2 dB. Now, we calculate the received power using previous formula. So, PT transmit power, it is given 1 watt, simply we have to convert it to dBm. GT, it is already in dB, given 10 dB. GR, it is 30 dB. Path loss already we calculated 170.2 dB, and LA, this term represents atmospheric loss. So, since it is a loss of 2 dB, we are subtracting it. So, putting all the values here, received power, it is minus 102.2 dBm, very small. Now, considering link margin equal to 10 dB, so then you see this is the received power, then PR minimum specified for the receiver, that PR mean value, it would be 10 dB down from this value, or 102.2 minus 10, it is coming in watt. If I convert it to watt, 6.03 into 10 to the power minus 15. Then we calculate RB, just use this relationship. Then RB, this is EB by N naught to the power minus 1 into S mean by N naught. So, put the values here, EB by N naught we calculated here 9.12. So, it is to the power minus 1. So, 1 by 9.12, and S mean we calculated 6.03 into 10 to the power minus 15 by 1.38 into 10 to the power minus 23 this is K into T. So, T system temperature is given 750 Kelvin. So, do not mix with the physical temperature. So, actual physical temperature it might be different. So, this is we call the effective temperature, effective noise temperature, or simply system temperature. We will discuss this topic later. So, it is 750 Kelvin. Then this figure as a whole it is coming 63.9 kbps. Even at 77 gigahertz for this given transmit power, if we need to maintain all this required link margin, let us say 10 dB, and if we consider all these values, then maximum data rate you see it is just 63.9 kbps. So, it depends on received power in presence of noise. So, SNR it plays very significant role. If you want to improve data rate, then we have to increase SNR. We do not have any other option. Now, till now we have discussed about the general characteristics, and we have some idea about now SNR and how any channel it performs in presence of noise. We will take more examples, and we will discuss about the effect of noise in details. So, before that let us consider a special scenario, because now people are talking about 5G communication, and it can be of course at any millimeter wave frequencies, but let us consider a typical scenario for 60 gigahertz band applications, because if we go for picocell, it is much easier to design or use at 60 gigahertz band. Then we can use that frequency reuse, we can utilize that frequency reuse between different cells. So, what are the advantages of 60 gigahertz band? First of all, throughout world it is unlicensed band, 57 to 63, 64 almost 7 gigahertz, this is unlicensed band, and highly secure operation is possible because of that high atmospheric loss due to oxygen absorption. Why highly secure? Because whatever I am transmitting, I know it can't go beyond a few kilometer. So, after a few kilometer nobody can listen to me. Not only that, if I use a highly directive beam, that means if the gain of my transmit antenna is very high, so any persons outside that they can't listen to me, because it is whatever power available outside the main beam, it is very less, and it is further being attenuated by atmosphere. So, we can say highly secure operation is possible. Then high level of frequency reuse capability, we can decrease the size of picocell and we can utilize this same frequency band over and over, can support fiber optic data transmission speed, whole 7 gigahertz is available. So, we can utilize almost whole of this band. So, sometimes that is why it is called 5 nines channel. So, you might have you might know the 2G spectrum distribution, 3G spectrum distribution. So, for each and every company the spectrum available it is very much limited, but if we go for 60 gigahertz band application, which you see it is unlicensed band, you can utilize the whole band and you will not disturb any other person who is a few kilometer away from you. So, you can utilize this whole channel, 7 gigahertz channel is yours. So, that is why sometimes it is called 5 nines channel, 5 nines usability. Then to some extent we can call mature technology, because now most of the components are available in market, and day by day the cost becoming cheaper, but also we face some other problems. So, let us discuss about those problems. First problem we will be facing is free space path loss, which is 20 log 10 4 pi r by lambda. So, r is the free space distance and lambda is the wavelength. Now, you see I am giving you some calculated values for this free space path loss for r equal to 10 meter. At r equal to 10 meter, if I calculate this path loss for 2.4 gigahertz channel, it is coming 60 dB. If I almost double the frequency to 5 gigahertz, so we have 6 dB more attenuation. Now, if we go for 60 gigahertz application, path loss is 88 dB. In this expression, we did not consider the absorption due to oxygen molecule. No atmospheric attenuation is here. Just because of the lambda value, the smaller lambda value, this path loss is increased from 60 dB to 88 dB, 28 dB higher. So, obviously, for a same signal power at the same distance, if I compare the performance of a 2.4 gigahertz channel with that at 60 gigahertz channel, what we expect? SNR will be much poor at 60 gigahertz. So, this is a problem for 60 gigahertz applications. We have some other problem, and we will take some numerical values, and considering this 28 dB extra attenuation due to path loss, can really any channel or any communication feasible at 60 gigahertz or not? We will see after a break. Thank you.